Hi, everyone. Thanks so much for joining us today. I'm Anthony Romeo with Occipital AI, and I'm joined here with Michael.
Yeah, hi everyone. I'm Mike Timofeo from Stäubli Robotics, joining Anthony at Occipital AI.
Great. So today we're going to dive into how AI can really enable robotics to do more, and how you can get the most out of your robotic system by utilizing AI vision. So a little bit of background about Occipital AI. We're north of Boston in the Bedford area. We have a explicit focus in the food industry. The reason being is that AI-enabled vision really lends itself to products that have a lot of variability. If you have a very highly repeatable part, like a phone that you can get a CAD file for, it's really good with traditional machine vision. When you have something that doesn't have a CAD file, like a chicken wing, everyone's going to be a little bit different. It really lends itself to AI-enabled vision and some of these deep learning processes to train a vision model.
Yeah, I haven't seen some of the standard vision companies do work with food worth before, so I think you got
Yeah,
on something here.
it's really hard because everyone's a little bit different. It's very non-repeatable, but that's exactly where we thrive, in those non-repeatable applications.
We're kind of the opposite, I guess. It's a mechanical solutions company. Stäubli developed the first robot with the internal tubes, which allowed us to go into the specialized markets like pharmaceutical and food, where we have the HE environment for human environment and the specialized coating to withstand the cleaners. And that's kind of where we found our focus is on these harsh environments, complicated environments, where we can add value to just the standard robot arm.
Yeah, I think you guys bring a lot of value in the food space and are certainly an established player.
Yes. And that, yeah, great segue to this. You can see the pressure washer knocking the robots. And that's, if you're familiar with some of the other people who do this, there's covers you put on the robot which get torn very easily. You end up with corrosion, risk of bacteria, possibly recalls, as we've, over the last few years, has happened quite a bit. Um, and I think really that's where we're strong, is in the proteins, dairy, convenience foods, bakery, where you're touching the product directly with the robot and you need to clean something up, like the kebabs shown there, or dealing with, raw avocados for the avocado toast, of course. But and anywhere where you would need to clean, where you're going to end up with a mess. And I think that's where we're kind of strong. And then uh, all of these are food, and so that's where we are together with you, where we've had the vision to try and find the part as it's going, because you're dealing with a more random object. It's biologic, so there's commonalities, but chickens go from like 4 pounds to like 12 pounds or something like that, right?
Exactly. And we're really good at, again, handling that organic variation. And I think both of us are in the efforts of food safety. You guys on the very easy to clean the stuff, and hopefully our vision systems can help find defects to pull out of production. So hand in hand, keeping food product more safe.
Yeah.
All right. So on the AI side of things, I think that AI has obviously really exploded recently. It's hard to kind of hear about anything without there being AI jammed into the topic. But I think that one of the reasons why it really hasn't exploded in the food space quite yet are kind of these three key things. So first of all is the training barrier to entry. And so it sounds great that you can just take an image and you train you label a couple images and everything starts working. But we found that if you have a few images, you run into this whack-a-mole problem where you might add another image to get it working the way you want it to. And that image that you added gets that problem to work, but then something else starts misidentifying. And so then you add more images over there. And really, to get a robust model that works, you need thousands, if not tens or hundreds of thousands of images.
Yeah,
And
no,
go
sorry,
ahead.
I experienced this personally. So as you're going through it, as I recall dealing with this with customers, where you've got someone sit there for literally hours and hours training images in. People may be familiar with the old solder systems where you would try and train it to recognize cold solder joints, this type of stuff. Far more repeatable products than food, but still a huge task to really get a learning system to build a true model.
Yeah, and it's super time consuming and tedious to do all of that labeling, but it's also super important because that labeling and training data is going to directly impact the performance of the model. So it might sound like, I just want to breeze through these 10,000 images that I need to label. But in reality, labeling those correctly will ensure that the model performs later on. So it's really important, but it's the current process. It takes way too long to be able to do that.
Definitely.
So I think the next point as to why AI vision hasn't really exploded quite yet is the lack of control that you have once you develop these models. So you might, if you spend all the time to develop an object model that works and it can correctly identify whatever product you're looking for, if you have a certain defect that you've trained, if you want to add any variance to that defect, kind of too bad. You've already trained it in with these certain tolerances. So if you say this chicken breast is high trim or low trim, that's like a binary good or bad, you're not going to be able to adjust that tolerance later on and say, this one isn't actually good or bad. This one's kind of on the margins. And if I defined 10% as good, it would be good. But if I defined 11% as good, it wouldn't be good. So not being able to kind of key in your application is a struggle people have when using these AI systems. And then finally, I would say that once you have something working and it's keyed in with your tolerances and it's working for you, how do you know if it's actually doing any good? And if it is doing good, how do you know how much money it's saving you? Being able to have a digital record of every product you're inspecting and being able to aggregate that information and be able to track a trend of, this machine is breaking down after 10,000 pieces of chicken. Or, our average size of chicken is 88 cubic centimeters. And because of that, we can change our packaging. It's being able to have all of this data and being able to justify value is really important. I think it's a step that's currently missing in existing AI systems.
No, that's really interesting because your ability to use the data not just for the specific task at hand, either quality control or pathfinding or something like that, but being able to track back almost like a predictive maintenance type thing now out of what you're coming up with. You could start to get trends and other information out of this data. You've got it, you can use it, right?
Yeah, and trends are huge. And then I guess another piece that I forgot to touch on is if you, in the food space, maybe this is a little less roboticsy, but if you see 5 burned corn dogs in a row, there's a really good chance that 6th corn dog is going to be burned unless you do something. If someone hasn't turned down the oil temperature or someone hasn't sped up the conveyor belt, unless some action is taken, you're just going to keep on getting burned corn dogs. And so being able to identify that and send a machinist signal, hey, we need to stop doing what we're doing. We need to turn down the temperature. It can really save you some money and kind of increase your overall yield.
Definitely. Yeah. I think there's other aspects of it that bring value to the whole production that aren't just in the initial machine implementation.
And so utilizing AI and kind of some new capabilities that Occipital AI is offering, I think we're really changing the paradigm in terms of training these models. We do not like hand labeling these images. We think it's very time consuming, very tedious, and it's honestly very error prone. If I'm labeling images at noon on a Monday versus it's 6 o'clock on a Friday and I want to go watch the Celtics play, my integrity of labeling is going to be very different in those two scenarios. So what we do instead is we will take a full 3D scan of the product that we're working with. Here you can see we're scanning some corn. You can see on the screen we have what the scanner has picked up already. And once we take that 3D scan, we have a full 3D asset that we can see in digital space. With this asset, we know all the dimensional information because we're using, again, 2D and 3D data. We know the width, the area, the volume. We know the circumference at the top of this piece of corn. We know the circumference at the bottom of this piece of corn. We know where there are defective areas. Here you can see we have some tip fill. So the top of the corn is looking a little bit gross. We're missing some kernels. And we know exactly how much of that product area is defective. So knowing all of this allows you to key in your robotic system to make more informed, more intelligent choices. Once we've scanned a representative number of product and we have all that dimensional information in these product assets, here you can see we're working with chicken and we're doing a synthetic data generation of some of the scanned pieces of chicken. Because we've scanned all of these pieces beforehand and we know all of the dimensional information, we're not taking an image and saying, label all of the dimensions of all of the pieces of chicken. We're saying, we know that there's a piece of chicken that is X by Y centimeters. Use that exact piece of chicken that is a real piece of chicken and generate it in 3D space with 10 other pieces of chicken that we've scanned in. We can program the system to do this hundreds of thousands of times without needing a person to go in and manually label everything. We can say, all right, here's our library of 30 pieces of chicken. I want you to drop 10 pieces from that library of 30, and let's randomize that and do it 100,000 times.
Interesting. So what parts of it, these are actual images of actual chicken you're working with?
Not images necessarily. We're doing a full 3D scan. So it's 2D and 3D data. So if we kind of go back up to this piece of corn that we have spinning in space, you can think of, we have a chicken model just like this, where we have a piece of chicken that we can rotate around. And we're saying, all right, we've scanned 30 pieces of chicken. I want to generate a scene and drop that piece of chicken that we already know all the dimensional data for, drop it on a conveyor belt from 5 feet up, and let's let everything settle. Because we know that we generated that scene with 10 pieces of chicken, we can use that once everything is settled down. We can take that image, feed that into the system saying, we know that there are 10 pieces of chicken in here, and we know that the dimensions of each piece of chicken are X, Y, and Z. And so that really allows the system to be trained quicker and more accurately.
So you're using real variable data to train it to find these objects in random events in hundreds of thousands of scenarios.
Exactly. It's like 30 real pieces of chicken to create 100,000 synthetic scenes.
Right. Yeah. As opposed to randomly adjusting the chicken imaginarily, which may create a chicken piece that could never exist in real life.
Exactly.
Interesting.
And so all of that allows us to generate pre-trained object models for our customers. So I talked early about the pain point of the barrier to entry in training these models. We fully understand that in the food space, not every food company has a dedicated team of machine learning engineers. They have a lot of operators that probably really know that food product better than anyone else. They know how to manipulate it. They know what matters to them. They don't know how to train an object model. That is outside of their expertise. So we offer our customers a fully trained model. We have the experts here. If you deploy our system, it should just work and be able to easily communicate with the robotic system like Stäubli.
Right.
With these object models, we bake in defects detection and identification. Not only are defects important, but being able to distinguish between defects is very important. Here you can see we have a tray pack, which looks good. We have one which is bad because it's styled incorrectly and it's facing 90 degrees the wrong direction. And then the other one has the membrane orientation incorrect. It needs a full 180-degree rotation, but is in the correct position in the packaging. So the root cause and the action required to remedy these two defects is different. And being able to distinguish between these two allows you to either optimize your upstream process or divert it in the correct way so that it can get to the person that knows how to take the right action to fix the problem.
Well, and prevent downstream failures, because as you go to put the final wrap on, product being out of place, you're going to jam the machine, type of thing. So yeah, it's not that there's anything wrong with the chicken. It's that it's going to either look wrong on the shelf or you're going to have a failure downstream. And how do we prevent that from happening? Now you've got that predictive feedback again, right? You're able to take that and say, if this happens every third or fourth tray, we know there's something wrong with the machine that places the chicken.
Exactly. And then you can go upstream, fix that problem, and then prevent the defects so that you're increasing your overall throughput. Exactly.
Right.
In addition to identifying defects, we can also identify pick priority. Again, for each inspection, we know everything there is to know about that food in which we're inspecting. We know the length, we know the width, we know how much overlap it has, we know what products it's touching, and defining different pick priorities can help optimize your throughput and increase just the overall system. So if you have a Stäubli robot arm that needs to go all the way across the conveyor belt and pick the furthest piece of chicken and then go all the way back the conveyor belt again, that's going to lower your overall rate, as opposed to if it was prioritizing the chicken closest to it, you could get more picks per minute, increase the rate, and you can define different pick priorities for different robotic systems so that they're all working in conjunction to optimize your overall rate. Maybe you have the most upstream system take stuff from the top of a pile so you don't have piled product later downstream. Maybe you have the furthest downstream system, just prioritize whatever the furthest downstream is. I got to pick that first so it doesn't fall off the belt. And maybe some of the middle ones you can have optimized to pick the closest piece to try to increase your rates.
That makes sense. I mean, yeah, you can do path planning based on your throughput and how many robots you have. Because yeah, commonly in these type of systems, you do have 2, 3, 4 robots because you have to make some high throughput on multiple containers. So yeah. And what are you using to pick up the different shapes? Because you're working in the robot envelope, correct?
Yeah. To pick up different, like the different products, or
yeah, to know how things are stacked on top of each other.
Yep. Oh yeah. So the way that we can pick down stacked product is we're imaging directly in the robot workspace. So a lot of traditional vision systems will image upstream, and that gives the vision system 1, time to process, and then 2, it can kind of sort out which pick coordinates to send. The issue with that is if you have overlapping product and you image upstream and then you take the top piece of that pile, you have no idea that there's another piece underneath it. Because we're imaging directly in the robot workspace, once we take that top piece of the pile, we will image again, see that there's another piece, and be able to pick that second piece and send those next coordinates.
Yeah, okay.
And again, kind of on why I think AI automation hasn't really exploded quite yet, being able to see all your kind of key analytics and knowing exactly how your system is performing really lets you understand how much money you're saving and how much the system is impacting your production. So here we can see that there are low trim defects and there are wrong side defects. If I was going to lead a Kaizen event and have continuous improvement to try to drive down one of these defects, I could spend a lot of time trying to address the wrong side issue. But I would think that that would be a waste of time relative to addressing the low trim issue. We can see that that issue is much more representative and much more prevalent. And having all of this data and being armed with this information allows you to make a more informed decision of where you should be spending your time to improve the process. If I could wave my magic wand and get rid of one of these, it would be way better if I could eliminate this low trim issue. And maybe you're thinking, well, the cost of the wrong side is tens of dollars, and the cost of the low trim is single dollars. And maybe that would be justification for why we attack the wrong side issue. But again, just having this breakdown and knowing the exact number of each defect and over time where these defects are showing up just allow you to make a more informed decision.
Oh, no, having the ability to build this database up in a product like this is fantastic. I mean, you've got now when you want to do your justification for a line change, you've got the numbers right there to show.
Very well said. And so training these models and all of these advancements in AI, what does that allow us to do from like a feature standpoint? Well, we can intelligently grasp products better. What does that mean? Here you can see we have two examples of apples, and in both scenarios, we would successfully grasp the apple that we're trying to pick up. But in the first example, we would be jamming our end of arm tool into two neighboring apples, whereas in the second example, we would avoid those collisions. So when we're developing these object models, we work in the food space. We are very aware that food is bruisable, is a living object, and we don't want to damage neighboring products. So all of these calculations are taken into account in our object models.
Well, yeah, and you can feed it back to the robot as it's moving, so it gives you the ability to pick that part on the fly, as opposed to, having to run that out of a pile. And as you mentioned before, if these apples move while it's happened, we can grab the next image again for the next pick, and we know that that apple turned or something. So you're able to adjust.
Yep. We can also, again, identify different defects. Here you can see we have pieces of chicken that have the correct membrane, and then the membrane showing up, and then the bad examples, we have the muscle side showing up. We would want to flip those 180 degrees so we have the nice side showing for all pieces of chicken. We can also do component segmentation. So we can not only look at defects, but we can look at subparts of various products. Here we can see the fat contents on various pork loins. Another example would be looking at the stick in a corn dog. We could get the stick length, make sure they're within spec. But being able to look at these subcomponents can, again, help you make smarter decisions on the robotic side. Maybe we want to send the pick coordinates for the highest fat content pieces first. Maybe we only want to send coordinates or filter out pieces that are below 10% fat, allowing us as kind of the eyes of the system to be able to make more informed visual observations.
Yeah, well, more information helps. If you used correctly, you can drive other things with it. We can do sortations. We can do like quality specs, like you suggested, or I think, yeah, the ability to, because really that is the big change in a lot of factory automation. It's having that information, being able to do more with it, make decisions on predictive maintenance or downstream quality, right? And you guys help feed into that, not just with the robot for the picks, but into the whole process.
Exactly. Yeah, both in real time and then having all of that information aggregated together as well. All of our models also take into account organic variation. We do work in the food space, and we know that every piece of food is going to have this organic variation present. So no need to have everything be presented in the exact same way and be exactly repeatable. If your birds are bigger or smaller, or your corn is bigger or smaller from one year to another, all of that variation is baked into the model.
So what kind of errors do you get? Like how accurate is the image processing?
In terms of detecting like the product that we're looking for?
Yeah, the correct product sizing, because as you get parts layered up, do you ever have trouble imaging that, or curiosity?
Yeah. Typically, like, I guess we don't, when we're talking about picking, we don't need to successfully identify everything every time. What I mean by that is if you have 10 pieces of chicken, all chaos, like in this example here, if
Yeah,
we didn't initially identify this piece entirely accurately, because it's being, there's occlusion and there's overlap on top of it, we couldn't pick that one if we tried right now, anyways.
right.
This one, however, might be a pick candidate that we would need to process and be like very accurate as we would be sending that coordinate kind of to the robot. So in terms of being able to process everything in the accuracy, the stuff that's on the top that we have a clearer view on, we're much more accurate. And then we can make these like estimated occlusion scores of we think that this piece of chicken has a certain dimension, but we're not 100% certain because this could extend only to here. This bone could extend all the way to here, and we aren't certain. Those estimates certainly have more variability. When it comes to the good product, I'd say it's very accurate. Again, because we're not just using 2D imaging, we also have a 3D sensor as well. We have all of the dimensional information to be able to correctly dimension the product.
All right, thanks.
Um, all of these innovations also allow us to, as we kind of have alluded to, handle this chaotic in-feed. So traditional systems, you kind of need a big question when you're scoping an application is what side is it justified on? How much space is there as an index between parts? With us, product can be overlapping, it can be touching, it can be any chaotic in-feed. We're still able to identify different products, send pick coordinates to the robot, and be able to pick down that chaotic bulk. In addition to handling the chaotic bulk, we can handle movement in the robot pick area. We've kind of touched on this a little bit with the apples earlier, but here you can see that Capri Sun really jostle as it gets picked. We grab another Capri Sun in the meantime as we're letting it settle. Once it's settled, we're able to re-image and then account for that movement and go back and pick it. Again, traditional systems and existing systems out there will image upstream, which allows the system more time to process, but it is completely blind to any movement in the robot pick area.
And so how do you handle the robot arm again when it comes into the zone? I think we talked about this briefly, but
yeah. So could you say the question one more time?
yeah, how are we handling the robot arm? Because you're taking images all the time, and
Oh, yeah.
working.
So because we're imaging directly in the robot field of view, if we were to just continuously image the entire time, there would be a lot of like bad images where we just have a robot arm right in the way and there's no usable data for us to process on. So we kind of have this little song and dance of we know where the robot is in 3D space. And when we know the robot is going to be blocking our field of view, we stop acquiring images so we don't waste processing time decoding images that are kind of worthless to us. Once the robot arm has moved out of the field of view and we can start getting good images again, the robot will start acquiring kind of as fast as it can go. We process all of those images. Once the robot comes back into the field of view again, we stop and we kind of go back and forth. So we're only spending time processing the images that have meaningful information for us. Great
Well, and
question.
once the robot gets in the move anyways, we need to have the point where we're going to so you can calculate, especially with a 6-axis where you have to do a vector approach or something. We'll need that data while we're on the fly, right? So at a certain point in the transition, we have to have the data, and then we're going to jostle the parts anyways that we just saw with the Capri Sun. So maybe having that data will give us, it's going to change anyway. So you not acquiring probably helps anyways.
Yeah.
Okay. Sorry to interrupt. I just was.
No, no worries. Good questions. Keep them coming. Uh, so again, here we can define pick priority. You can see which pick is being prioritized here. We have some different options. Maybe we wanted to prioritize the one that is closest to the belt. Maybe we wanted to prioritize the one that is in the center of the field of view. Maybe you need to prioritize ones that are furthest downstream. All of these different pick priorities can, again, kind of be utilized together to make sure that your throughput, whatever desired rate you need to achieve, you're able to hit that rate.
So, are you able to sort, say, if your pick priority was size, would that
Yep.
be one?
Yeah. So in here, if you were to go into our recipe builder, we could, when you go into the sort field, there's like a bunch of options and you can bubble them up or bubble them down. And it'll say, this is the most important thing. This is the least important thing. And in addition to sort, we have like a filter option if you just want to completely filter stuff out altogether. In that sort option, you could say, I want to prioritize the biggest volume or the biggest area. And what it would do in this example is, I don't know off the top of my head which the biggest one is, but if this was the biggest piece, it would send this one first. If this was the second biggest piece, it would send this one second. If this was the third biggest piece, it would send this one. If a new piece came that was bigger than everything, it would put that at the top of the priority, send that one, then go to the new second.
Okay.
You could also, if it was, let's say, I just want to go from biggest to smallest, you could say, for this specific robot, I want this one to always pick within 90 grams to 120 grams. And you could have the next robot with a different one that's always 120 to 150, and the next one that's always maybe smaller. And with all of those together, your total weight size will always be between X and Y, and you always have a big piece, a medium piece, and a small piece. Really, you can get as creative as your mind can imagine, and we can prioritize that pick priority and make sure we're sending the next pick correctly to the robot, or maybe however many picks it needs queued, we can send that information. Also, when we're building out these object models, we're able to take things into account like lighting variability. With traditional vision systems and even some newer AI systems, when you're hand labeling all of those images, if all of those images were darker or lighter or brighter, it can completely change the training results. For us, we say, all right, let's generate 100,000 pieces of chicken that are going to randomly settle with this lighting specification. Okay, let's do it again, but let's simulate a brighter lighting environment. Let's simulate a less bright lighting environment. All of that is something that we can take into account using synthetic data generation, where traditional approaches, you would just need to physically go in and get all of those images again, and then you would need to label all those images again, and then you need to go hire someone because that person labeling them hates their job and quits, and you need to train that new person. So it's very nice to be able to bake in that lighting variability synthetically as opposed to aggregating all of those images.
Now, I've had installations in my history where, with more traditional systems, where they were into plants that had skylights, and that plays havoc with things. Ended up having to build light boxes, right?
Yeah, it's crazy how much a cloud can ruin a facility that has a skybox. And so not only lighting variation, but because we're able to iterate quicker, we can bake into account things like conveyor belt variability. So if you are working with a blue conveyor belt and we have to retrofit it, now we have a white conveyor belt. With traditional machine vision and even other AI systems, you would again need to go back to the image aggregation part, take all of those images with the new background, label all of those images with the new background. For us, nope, the product isn't changing. It's still the same corn. It's still the same chicken. It's still the same corn dog. It's just the background has changed. We can run that data generation with a new background.
Interesting. Yeah. So this
Um,
is a real world example, you guys, with the corn that you played through with the different backgrounds to try and simulate for somebody.
Yep. So when we're training our models, again, I kind of mentioned earlier on like the speed complexity, the more that you have baked in, the longer it takes to process. So we try to strike this balance where everything you're seeing here is part of like the basic variations training set. So we
Mhm.
want to be able to, if the conveyor belt is still blue, but it's a different shade of blue or there's a stain, we want to be able to identify it. But we also know that if a customer has a certain blue conveyor belt, we don't want to, in training the model, have the same number of green conveyor belt images as their representative blue conveyor belt. So we kind of over index and we over fit on we're using a blue conveyor belt. So we want to have most of the training data be representative of the customer with this training, with their belt. But we also, if there is a little bit of variation, want to make sure that we can account for that. And we use a bunch of different backgrounds, as you can see here, for that training. If the customer were to say, okay, blue conveyor belt's out, white one is now in, we would tweak down the
Yeah.
number of blue ones, tweak way up the number of white ones, get them a model that will perform better for their new background, but still have all of this like baseline variability data baked in the background.
Okay. Yeah. Thank you.
Great question. And so all of these AI innovations are essentially allowing the vision system to be a little bit smarter and have more data to make more informed decisions. And we can ultimately use that data and that information to feed into the robots so that they can make more intelligent picks and tackle applications that maybe weren't previously solvable.
Well, which brings us to how it all ties together, right? I mean, the robots, the uh, physicality. So you've got the gripper, the your neurons and everything, and the cerebral cortex, I guess, and then the hippocampus and everything is the AI, right? So you're using the vision portion of it, driving it into the hippocampus, which then drives the data down, just like how we try and think where we're going to go. You've got that other level running on top of it. So, sending that XYZ and vector and velocity and everything that we do in our person, right? So you're
Exactly.
just taking that other level on top, I guess, for us, right?
It's a great way to think about it. Yeah.
And so, yeah, I mean, being more familiar with regular vision systems where you're even the AI, as some of them call them, it's just a learning system that's, like you said, you're teaching all those things. So you often have to have a trigger. It strobes the image. We send that. It calculates out where it's going. You send that data to the robot, socket or Ethernet IP or whatever, and now we go and acquire the product, right? So if something changes in that time frame, we go down to a spot and it's not there. Where because you're doing it so quick, I think that ability to plan more in real time. I mean, not true real time, but it's closer to real time where you're compensating for changes. We're not doing it, 2 meters up on the conveyor and assuming that it's still going to be in position, which works okay with a lot of products, but not always with food, right? So
Yeah. I
I think
think
that,
food is always kind of clumped together and is very prone to moving and being jostled.
well, yeah, friction from rubbing on the side of the conveyor or any other thing that's going to vary, any other variability that we can maybe get out of that. So I mean, the robot because we're in the world of atoms, you've got known cycle times. And even though Stäubli is faster than a lot of other brands, you still have that physical motion that's happening, right? So having the ability to send the signal closer to when we're picking it up really adds to the ability to get something like a chicken breast and put it into the container as opposed to, we're not picking like molded plastic parts out of a tray, right?
Yeah.
So oh, hey, perfect example. Chicken in a tray. but
Yeah. So here we have a little video example of an application we've partnered with Stäubli on. So we have a bunch of bulk chicken that we're ultimately packing. So this final part of the process has the chicken has already been singulated and it's the right orientation, and we're passing it into a tray, making sure they're alternating like long, short, alternating direction so that it's aesthetically pleasing for customers. And then to get to the singulated piece on the conveyor, it starts in bulk. So all of this is just like dumped onto a conveyor. They're all touching each other. They're overlapping. They're neighboring each other. We're able to, as you just mentioned, in real time, identify a piece of chicken, send the pick coordinates to the robot, get that pick, all while we're looking for the next pick of a piece that is not currently in motion. Here you can see we're just orienting the chicken properly. So if the membrane side is up, we just let it go and keep the same orientation. If the muscle side is up, that does not look aesthetically pleasing. So we want to flip it 180 degrees. So we let it fall off and do a full 180 rotation. Which the final result is a very nicely packed piece of chicken, all done by this beautiful Stäubli robot.
Hygienic robot, yes, because you're going to have to clean this down afterwards. It's chicken. But...
Definitely don't want salmonella on the robot.
No.
So AI is extremely powerful and a really awesome tool for vision, specifically for inspecting food. And a lot of people get a little bit overwhelmed on how do I get started? What do I need? I don't have a team of software engineers. I can't use AI. Well, for us to get started, we just ask that you fill out our basic requirements document. We really just want to know what product we're working with, how big it's going to be, what's the biggest size, what's the smallest size, what type of rate are you trying to achieve? Is the product going to be overlapping? Is there going to be space? Is it going to be indexed? And once you get all that information, we can get started. We can go to the supermarket. We can buy that food. We can take a 3D scan. Once we get a working object model, we can send that to you and we can start validating against your product. But we out the door send a working object model because we do all the training in-house. We don't need to go on site to get a lot of images to start our training process. We will go, and if we're gathering images, it's more of a validation to make sure the system is performing to your desired specifications.
So if a customer had a change in their product, like beef burgers to veggie burgers or something, which has a finish size difference, would you be able to generate the model remotely and send it to them? Because I'm looking at the picture, that's why it came to my mind.
Yeah, no, good question. Depending on how different the models are, depends on how much work there is. We found some success in chicken legs versus turkey legs because there's a lot of similarities between them, and it's really more of just a size thing and scaling. We have found that if you are trying to identify two different types of cereals, it can be very hard from like Golden Grams versus Lucky Charms because they're very different products to look at.
Right.
So depending on how much overlap there is, depends on how much effort we have for working on a new model. But I would say a general rule of thumb is if we develop an object model for regular burgers, I would advise using it for regular burgers and talking to us, not to say we couldn't generate an additional model to do veggie burgers, or we could generate an additional model that can do veggie burgers and regular burgers. But I would not advise taking a model that is designed for regular burgers and trying to apply it to some other products.
Understood. Yeah, we use a similar process, though it's a little more, let's say, labor intensive. So when our customers come to us for a model simulation, our TSS group has to get either a layout of some sort from the customer. Usually we want a tool drawing, a product drawing, and then we can work out the kinematics. We can do the simulation to see if we can do the 50 chicken wings or the 60 veggie burgers or whatever. And minute that the customer requires with the tool they've required, planning the trajectory, the process sequence, that type of stuff, what inputs we have. So we need a lot of this stuff to come to us from, say, somebody like yourselves or your customer. And then we'll, put in kind of standard times and develop like a 3D simulation that then you can work, like you can see as a working model. We can tweak, we can run it through optimized labs so we can see if there's any issues with the robot, like high stress on a joint, whether we can speed things up, or you can like smooth the flow, or maybe there's a small change to the machine that can make the robot work a lot more efficiently. And so we're able to do a lot of that in-house on our SRS software. And for a lot of integrators, once they're familiar with it, they can do that as well. And that's kind of similar to what you're doing, but we don't get to go to the grocery store and buy the product necessarily.
Yeah, I think that 3D modeling is certainly a powerful tool that has been made even more powerful with recent AI development. So whether it be for developing food object models or plotting kind of the flow of robotics and everything. It's
Yeah,
very
no,
cool.
it's a lot of change from the drafting board, right? But,
Exactly.
so I think this really kind of brings us to the loop at the end of all this, right? Where you're taking your image, you're helping the robot work more efficiently. We can do quality, we can process for defects, we can look at yield improvements, quality and compliance. So we've got the camera taking the image, sends it to process it while the robot's moving to go to the next point, right? So we know where to go. We can pick it more efficiently. You can get higher throughput. We can pick those defects out. You can leave things alone that you maybe want to go downstream to a defect. So all that ability to do more than just a simple image recognition, go pick and place, and then something else has to sort it downstream.
Makes sense.
And we've talked about this a little bit already, the whole ROI labor thing. So we see this internally. We've got the, Europe has a little more automation than North American food. There's higher labor costs, drove it earlier, the hygiene standards. And then we're pushing it here in North America, especially since COVID. We had all those labor shortages and stuff. So there's been a lot of emphasis on adding robots to some of the food processing plants. And also we're able to leverage some of the solutions we've seen in Europe, or, come work with partners here who have come up with new designs in North America like yourselves. And then we see Asia is probably a little further out. There's been a little talk of it. I think there's, some of the markets obviously have done automation like Japan and that, but, for us, it's North America is the main focus at the moment. And we do have quite a bit going on in the food area, given our history with that. And I think the helping customers get that payback on the machinery, because, that drive for efficiency and get the cost down, especially in the current inflationary environment.
Yeah, there's certainly a pressure to keep costs down, and that often means automating.
Yeah, labor costs are going up, right? So,
yeah. So if I'm going to some trade shows this summer, is there anywhere where I can see you and learn more about this?
Yeah, I mean, we're at Automate, so June 22nd to 25th, booth 1801. Come and see us. Come see. Talk about things. And if you've been watching the background all along, I'm just going to do a pitch for something that isn't quite connected with you, but we've got our AGVs there, and another product that Stäubli offers in conjunction with the mobile arms. And we can talk about occipital and the solutions you guys have for the food industry.
Awesome. Look forward to seeing you there.
Definitely, yes. Yeah, well, you're coming to the partner event. We'll have a drink when you're there, right?
Sounds good.
Thanks, Anthony.
Thank you so much, Michael.
Have a great day.